Hi, Vix. Thanks so much for having me here, and it's such a pleasure to... I've never spoken in front of a crowd of animal behavior scientists before, so this is going to be new, and I'm very excited for the questions that I'm going to receive. All right, so this is, first off, work with many folks here, including Seth, who is somewhere floating around. As you can tell, it's fairly interdisciplinary because this is a project that involves a lot of applications to, so this is going to be human sort of institutional design and human collective behavior. So a lot of it is based on institutional design frameworks within institutional economics, from the law, and from different parts of, let's say, computers in society. So that line of work. So, quick overview of the plan. So I'll give first off, some background on institutions and governance as I understand them. It may feel like too much. Probably in reality, it's too little because as I'm coming into this, as a computer scientist, I've realized to myself how much I really didn't know about this work. I'll talk a little bit about this idea of CAD for governance, or computed-aided design. I'll introduce compositional game theory as a certain kind of mathematical framework that can be used to ground CAD for governance. I'll go through a bunch of examples, at least 5, maybe a few more if I can squeeze them in. And then, let's just think of it as therapy for myself. I will complain a lot to you guys about all the problems of trying to build this in the real world because it is incredibly annoying and frustrating, but sometimes rewarding to actually design real-world institutions and get them to float and work. And then finally, I'll end with maybe a little bit, step back and talk a little bit about what is the sort of bigger story that I'm trying to tell about code, about programming languages, this idea of CAD, and why it might matter in our world today. Okay, so let's start with a conjecture. So this is from Elinor Ostrom. For those who don't know Ostrom, she's Nobel laureate in economics. And Ostrom begins with this idea that there exists a set of shared and essential building blocks from which any governance system or institution can be built. So in this sense, a governance system, I'm going to define it as a kind of set of persistent mechanisms in institutions. And once again, we're talking about human institutions here, that regulate the behavior of a set of agents. I'll just say it's kind of like a funny question. Whenever I sort of look at this, I ask myself, a similar question. For all possible sets of building blocks, is there at least one governance structure which can be built from that set? It's like, oh, maybe we'll dig into that question a little bit later. So, but maybe let's build a little bit more intuition for what governance is, or at least for what I mean about it here. So governance is oftentimes thought of as a form of control. So control specifically over human behavior, regulation, penalties, taxes, exile. So let's say, take the example of Facebook. If you use racist language in a Facebook post, you might be reported. If you repeatedly use racist language, you might be banned. And if your racist Facebook post contains a credible threat of violence, you might get a visit from the cops. And this is a photo, I think, from like 2015. So you can't post racist content or you'll be banned is a kind of law on Facebook. But laws are really only the most obvious examples of governance. Norms are another. So norms are rules which are enforced by the community. So you should not post racist content or you'll be ostracized by your friends is a kind of norm. And markets, on the other hand, are a different sort of modality of governance. They set an explicit price on behaviors. So if all the racist content on Facebook causes people to cancel their Facebook accounts and move to TikTok, then that would be a kind of indirect way in which the market regulates speech because it creates a financial incentive for Facebook to suppress racist content, right? Interesting how that incentive changes over time. And finally, code, or architecture as it's sometimes referred to, directly prevents behavior, certain kinds of behavior, especially on these kinds of digital platforms, by making it impossible. So for example, Facebook has various kinds of AI tools that make it so that racist content is effectively just never shows up. It's not, doesn't show up in your newsfeed. So this kind of leads to three broad points about governance, right? So governance writ small is about control, but governance writ large is, in these cases, really about designing for collective action. So an institution or governance system is a setting and a design for collective action. Now, designing governance systems is really freaking hard. In the real world, you can't just plug wires into each other where it's sort of like, this is how it's going to work. You kind of have to work with the people who are in these communities to figure out what the actual system needs to look like. So the contentious claim here is that people have to design and evolve their own games, and this suggests that we need to give them the tools that help them design their own institutions and forms of governance. Lastly, doing governance is really a kind of work, and it's, I should say, like expensive work. I think when we sit here and think about, democracy, or this kind of voting regime, or let's say this deliberation mechanism, it's very easy to sort of stand back in that designer's kind of chair or philosopher's chair and think, this would be really nice. But in actuality, all these designs impose different kinds of costs on people that need to be shouldered by people in order to make these kinds of decisions and interact with each other to basically like agree on the text of a proposal. And this is actually extremely burdensome and costly for many people. And this is something that is really important when you're thinking about the designs of these kinds of systems and trying to realize them in practice. So what then do I mean by CAD for governance? So CAD, so one way of thinking about this is that it's a modeling tool for designing more integrated, multi-stage, hierarchical, and especially more modular kinds of mechanisms and institutions. Ultimately, the idea here is that we want different institutions, small pieces of things, to play with each other in order to realize some sort of global effect or result, right? So if I stick together, let's say, a compensation clause in a contract with some sort of liability, that these things work together to create an effect that looks something like, this is going to be a productive employee, right? Or this is going to be an employee that feels safe and trusted and respected in their role. So it turns out this is a really, really popular idea in the literature, especially in the social science literature. Leonid Hurwicz, one of the founders of mechanism design, called for this. Pretty much explicitly, I think I don't know if the citation is in the right there, but Elinor Ostrom called for this. You can see this calls for this in a lot of different fields, including, I can't be the one to sort of name this citation, but there is a citation actually in the animal behavior literature also calling for a kind of CAD for governance. And I'll just mention, so a lot of these sort of citations are from like maybe the 2010s, but very recently we've been working with some folks at DeepMind on kind of AI safety questions, which also directly call for this kind of CAD for governance. How do we build scalable institutions for oversight, for reasoning about these kinds of large social institutions? So let's think about some candidates, right? So we have first of all, and perhaps most logically, game theory. But game theory isn't really made for this kind of work. So mainly game theory focuses on toy models. So I talk about things like auction, spectrum design, auction design, compensation packages. It's more designed for what we think of as like pencil paper. So being able to get analytic results out of things. It doesn't really allow us to come up with rich descriptions of objects and institutions in the world. It kind of assumes that the world is as simple as the model. not that the model is as complex as the world. To put it in another way, game theory is really written and designed and created for economists, or maybe microeconomists. What if we try to redesign it or think about it as ways of thinking about society? So this actually happened. So this is a picture of an action situation. So this is a game theory inspired framework or formalism from Elinor Ostrom and many of her collaborators at the Ostrom Workshop in Indiana to kind of come up with a framework for thinking about these more real world, more realistic depictions of social institutions. So I'm not going to go into what all these particular words mean, but the point is this is kind of like a schematic description of any kind of arbitrary social institution or situation. And the key thing for me is that you can design the behavior of what's going on in each one of these, let's say, modules, actors, information control, by putting in different rules. So you can add in scope rules to potential outcomes. You can change the payoffs and the net costs and benefits. So it's this kind of, it's both a picture of how to think about social institutions as well as a framework for intervening on them, or at least kind of modularizing the way we think about intervening on social institutions and systems of governance. And you can sort of go further into this. The reason I put this slide in, and specifically this part, is it's kind of important to understand how action situations evolved, and this, like this idea of making game theory, turning into something that looks more compatible with the real world, is to understand that the way action situations actually got used in practice is very much in kind of from an academic perspective for the purposes of analysis, the purposes of, let's say, taking a bunch of ethnographic data that's collected by a bunch of PhD researchers and using that to sort of to order that into a set of relatively well-formed sort of observations, and then evaluating those things, and then generating theories out of them, right? So it's still in many ways a kind of academic practice, or an academic framework for research, as opposed to something that's gets used, let's say, directly and implemented in the real world. There's a lot of further development in this line of research. So this is from McGinnis, the idea that you can sort of like create networks of these action situations that interact with each other through different kinds of institutional statements. These are essentially, once again, just like roughly natural language statements stating like how action situations work and sort of different sort of components and properties of them. And then you can relate them to other action situations in order to sort of stitch them up together. The problem with that, of course, is that this is still all very qualitative. It allows us to sort of start thinking about how different kinds of institutions and systems of governance interact, but not in a way that helps it scale. So just to review, so we have some candidates for CAD for governance. So we have game theory as it's now, which is has exponential growth in terms of the kinds of payoff matrices we construct, and the actual real systems have way too many equilibria to actually evaluate and to optimize for. And generally speaking, and this is a complaint that my collaborators have all the time when talking with traditional economists, all the economists and the game theorists seem to be really, really preoccupied with solution concepts versus the kind of need that's really drawn from a social science perspective to actually even start to describe and prototype these kinds of institutions. From another strand, we have these action situations, which are, once again, inspired by game theory, but they're not really formal enough to implement computationally. It's hard to scale these kinds of tools and frameworks.
Josh, could you explain what you mean by the last, that not yet formal enough to implement computationally? So what does that actually mean?
Yeah, so actually, maybe the next one. So do I have this? Analytical, ecology of games. So this is kind of referring to some work by Siddiqui in France. So the most sort of recent versions of action situation holons is, at least I think of that sort of line of work as resulting in this institutional grammar 2.0, which is kind of like a way of taking institutional statements, which are traditionally just like ethnographic statements from PhD researchers located in these kinds of environments, right? They go to like Nepal, or they go to like Southern California and look at the fishery stock, and they ask like people, basically converting those kinds of ethnographic statements into things that look more formal and kind of computational. So you can sort of like just think like, I have a bunch of statements which are converted into something that's interpretable in a spreadsheet, and then I can sort of do some analysis. And there's been an attempt to make them more computational in the sense of like, I can turn them into something that looks like a domain-specific language, and then translate those things into then like active code. Like I convert statements into, here's an institution that I can implement. In practice, it doesn't get close enough. It's not actually a formal domain-specific language in the sense of like, here's like combinators, operators, and that's exactly kind of what we'll go through and why we need that. Yeah.
So yeah, two conceptual points. The first is, UCAT for governance, at which scale we are talking, like is it a city or a whole country? Yeah. And how big this is. And the second thing, how can you empirically test of this, given that there is a lot of...
How can I what?
Empirically test some of this, given that we have a lot of legal hurdles to access people, transactions. Some other country, we know that, some other countries have full access. Like Singapore did experiments on citizens, but they are very transparent to the government. I highly doubt that this would be possible in Western.
Yes.
So many laws to transcend.
Yeah. So in many ways, I've become more of an engineer just by the nature of like trying to get these experiments to run. And in practice, I try to avoid working with governments precisely because of these like the complexities of getting past the law, like understanding like what the kind of liability, consent, and I'll talk about a little bit later about a lot of the work, at least that I do, and many of my collaborators do, is really focus on kind of in online communities, right? So there are still obviously consent and sort of ethical questions, but they're much, much easier to deal with. But you can still reach like scales of...
But in the US, it's much easier in Europe. You cannot even combine...
Things are easier in Europe?
In Europe, it's much more difficult in Europe because you cannot combine even, like if you have Facebook data and Instagram data and others, you cannot collate them. So I think with these barriers, we have no hope in... I would love that this experiment happened, but legally, it's a nightmare.
It 100% is. There is a huge rabbit hole, and I have lots of thoughts on that, but it's a little bit kind of orthogonal to the idea here. But I'll say that in terms of scale, so you can take these things, and they have been applied to, let's say, scales of billions of dollars and tens, hundreds of thousands of people, technically. They are not, however, I was talking to someone else earlier, they are not intended for like solving global governance kinds of questions around, let's say, like climate change, right? Those kind of macroscopic kinds of challenges, hopefully we can get there, but this is trying to scale up from like 2 or 3 people games to things that look like, I don't know, 1,000 type, player games. All right, I'll just say there's a lot of different work. Okay, wow, I need to go a little bit faster. So I'll just say there's been a lot of work along these lines. Many of them start off from kind of a game theoretic starting point, and then try to go various ways to sort of different kinds of formal approaches, text-based approaches. In many ways, the issue here is that they're either not expressive enough or not formal enough to kind of get to that scalable kind of representations, what we think for like a CAD for governance. Okay, so let's imagine then, back to the kind of the pitch, a game theory that was bad for proofs. So economist, not going to love it. It's not intended to talk. It's not for solution concepts. I'm not sort of trying to say like, oh, this isn't actually clear. This is the best one. And it's not strictly a miracle, but it is rich enough to describe existing complexity. It can highlight structural commonalities, and it can capture different systems of games. And that leads us to compositional game theory. So game theory, as we know, is a kind of like theory of interacting rational agents. I'm not going to talk about rational here, and that's a separate kind of orthogonal conversation. The players make observations, and they make choices. The choices of all the players together then determine a set of payoffs that is assigned to each one of them. Locally, you can think of that the players act to maximize their payoff. This is kind of what we mean by rational in this case. And globally, there are equilibriums of how they interact. So this is kind of a quick review of game theory. And open games is a new formal language for game theoretic reasoning that comes from around 2018, but it's really been active in sort of, I suppose, my part of mathematics since the kind of late 2000s. And specifically, it also includes a software implementation for game theoretic modeling. So an open game is exactly this. So a good way of thinking about it is that there is a set of inputs or observations that go into a game G. And what results is a set of plays, Y. This goes into some sort of, let's say, other set of games, which then returns a utility, or a set of utilities, really, though this could be like kind of an arbitrary kind of, let's just say, set of utilities, or something that looks like utilities, functions like utilities. And the game then sends further utilities backwards in time to previous games. It's, in some sense, a very simple formalism. I'll just say that this kind of thing is designed in broad generality. So even though we often think of R as like real values, these can be actually very sort of kinds of structured inputs as long as they have some level of like, I think it's like just like any kind of partial orderly any kind of partial order on these structures works. Technically, underneath the hood, these are actually categories. I'm going to be very, very light in my usage of category theory here, but these are certain kinds of mathematical objects defined in terms of objects and morphisms, or the good way to think about it is just arrows. And there's underlying these morphisms, you can define them as sequences of different kinds of objects. So there are the strategy profiles of G. There's play functions, co-play functions, which kind of go backwards in time, and best response functions that sort of say this is the most rational sort of play of an entity. I'm going to sort of like be a little bit hand-wavy here because the math, or this particular definition is not the point of this presentation. You can think of what's really going on here really as just mathematicians cosplaying as computer scientists. What do I kind of really mean by that? So effectively, what I'm really giving you here is a recipe for building programming languages, right? This is, when I say compositional game theory, you should really have that model inside your head. So I take simple open games and I stick them together using lots of different operations, I'll talk a little bit about what those are, into bigger open games. So they have, oh right, I just realized, am I supposed to stand in one place? There's a set of atomic building blocks, so decision processes, sort of computation, which is just like think functions. And then there's a set of relatively simple composition operations like sequential composition and parallel composition. There are actually a bunch of other operators I'll talk about a little bit later. But the point here is like this recipe or this kind of approach has been done many times before in the creation of different kinds of programming languages. Basically, it's a thing that you can do anytime you have a piece of math that lives somewhere else. Let's say the lambda calculus, or let's say all the math that lives in quantum mechanics, right? You think, I kind of want to do computation with this stuff. Like, I want to stick them together and lots and lots of them together and create programs out of them, right? These are things you might want to do if you want to create like functional programs, or if you want to do quantum computing. You think like, what kinds of programs can I run on an actual quantum computer? I'll just say the word category theory one more time, is a recipe that you can use to do these things. It's sort of like the obvious thing, or practically the thing you would almost have to do in practice implicitly if you were going to create a programming language out of some piece of math. So the results are things like Haskell, which is the functional programming language, and measurement-based quantum computing, which is a certain kind of quantum computing sort of like framework or paradigm. And all we did is maybe the very, very simple sort of one-line version of what compositional game theory is. It's that applied to game theory, right? Game theory is a piece of math, and I want to turn it into something that looks like a programming language. In practice, so these are things like parallel composition. I have G1 and G2. I just stick them together to, or in this case, tensor in the category, to form a kind of a tensor version these things are happening in parallel without interacting, right? If I wanted to stick one after the other, so G and H, I just do them through these kinds of simple operations, right? And I can chain these operations, many, many of them together to form much larger games. So give you an example. What does the prisoner's dilemma look like? Well, it looks exactly something like this. So I have like player 1 and player 2 here. This is a simultaneous game, so you can see there's a tensor. Player 1 plays y1, player 2 plays y2. This is a utility function, and it just returns a reward to player 1 and player 2 based on their plays. It's a very kind of structural way of thinking about game theory that's designed to be, once again, descriptive, and in this case actually pictorial, rather than focusing on some specific set of solution concepts or indexing very, very sort of like, perhaps way too much on the design of this utility function. And you can sort of compare the standard representation of game theory with the way that we think about it compositionally. So once again, this is kind of this extensive form, where I'm sort of looking at a bunch of trees, and then these things dump into sort of rewards. Whereas here, I have this sort of more compositional approach, where I'm just kind of stacking boxes together in different ways. And of course, the boxes represent, concrete programming artifacts at the end of the day. I'll talk about branching a little bit later. So importantly, all this work that I'm sweeping underneath the rug here, but all this work allows you to build in a kind of like magical way, I think, given how hard it is to actually like write working programs and working programming languages. It just allows you to build really nice, clean domain-specific languages. So we wrote an open games engine written in Haskell that allows you to build up these models really quickly, analyze them interactively so you can kind of query them. Has a bunch of automatic tests running in the background that checks like, is this a well-formed thing? And even integrated with certain kinds of ML frameworks. There's, of course, a lot of missing features. So much work. All right, how to represent games in the engine. So there's a bunch of application kinds of questions, and we'll be focusing mostly on the applications. I just wanted to sort of add these citations here just because there is a lot of mathematics that I am, once again, sweeping under the rug here. There's the original paper from Ghani. There's work by Jules Hedges, which is in many ways the originator of this work, on ways of representing them as lenses, which is a certain kind of mathematical kind of object. There's work on Bayes-Nash, which was by, I think, James Balt as part of his PhD thesis in 2019. And then there's like further developments on graphs and their relationship to learning. So there's quite a bit of mathematical work that was necessary to make any of this, or certainly some of the applications possible. Right, I'll kind of skip. I think I already talked about the engine a little bit. I can skip this slide. So this is what things actually look like. It's actually nice and cleaned up. I kind of wanted to show you guys what the original code looked like, which looked terrifying. But it's been, after a few rounds of editing, it has been nice and cleaned up. So all you should do in order to program a game G is you sort of define what the inputs are, and these are, in some sense, just sets, right? What the feedback is, the output, and the return, and you kind of define an operation. In this case, I'm not going to, what we call a dependent decision for player name. So let's go back to the example. So in this case, programming a prisoner's dilemma in this case is just a matter of stringing together a bunch of these atomic units, decisions, effectively. You define a cooperate or defect as the possible sort of outcomes. There's the outputs of the decider, of the players, and then same thing for player 2. And then this is the thing that comes back. Of course, I'm not defining the numbers in utility function, but they're basically just inputs or the returns here, the player off payoff to player 2 and player 1, right? So it's very, very straightforward to actually create any one of these games. You can kind of change them together into much bigger things. Okay, so let's run through examples. Like, what do I actually mean by this? Like, why does it matter? So you can stick these things together to form, for example, this is an example of a relatively simple multi-stage carbon credit game, right? So any one of these, by the way, is going to be basically the subject of maybe like a paper in a single sort of game theory paper. So in this case, I have like carbon credits, right, or carbon permits that are assigned to a set of firms. These are allocated to firms, and then the firms, and there's effectively a kind of allocation game where the firms might pay for these things, right? Or they might submit documents, like this is how much I do, along with some money, and then there's like kind of allocation of how many credits that they actually get. The results of this allocation then goes into a production game where the firms, in this case, it's not anything competitive. They just independently sort of make stuff, right? And then they sort of use up the carbon credits, but they might have some left over. So there's a resale game, which the permits serve as inputs to these firms, which then sell the permits, any excess permits, to each other, right? And then this resale then goes into another round of production. You can imagine this keeps on going, right? Kind of iterates. So this is just a very simple kind of illustration of some, this parallel composition between firms, as well as the sequential composition of these like smaller games, as well as, of course, the substitution that we can do between these production games, resale games, and allocation games. Right? And the basic argument of the paper, just to refresh, is that this kind of work is really useful to social scientists, even though it's really not useful to economists. You can apply some basic software engineering principles to social designs, which leads to easier prototyping. And plus, here's a bunch of citations. So here's another example, shared integration. So this is an example sourced directly from the sustainability literature, in particular from farmers in Nepal. In this example, what we have is a set of farmers who have plots along a shared water canal, right? And then what we have is a situation in which, they can choose to decide like, oh, I'm going to try to consume as much water as I can. I'm going to do what is called cracking, or I'm going to, flooding, or I'm going to consume just enough to make sure my crops grow okay, while making sure that there's enough water for the remainder of the folks there, down the line or down sort of at the end of the canal. There is a kind of norm for more equal distribution, of course, but there are lots of incentives for effectively cheating, trying to consume as much water as possible. There are lots and lots of variations for how we can solve this problem, right? So there's just, there is no any kind of additional governance on this. You just do what you can, and of course that gets the equilibrium result is effectively exploitation. You can impose different kinds of monitors, right? You can just say there's a third-party monitor, but they're unpaid, but in that case, they're susceptible to bribes. They may not be incentivized to work. You can get them to be paid through, let's say, the state hires them, like some third party just like pays them to do it, but then it's like, are they still incentivized appropriately? They're still susceptible to bribes. They can be paid from penalties, but then that incentivizes going the opposite way, right? They might penalize you or do bad reporting just in order to get more penalties. And there's like lots and lots of different sort of variations of how we can approach solving or designing a solution for just this really, really simple kind of collective common pool resource problem. So this is an example of just like for 3 farmers of the kind of payoff matrix that you would need to work with in this traditional representation, right? Between cracking, so that's not consuming as much as you possibly could, versus flooding. If you had an external monitor, suddenly your payoff matrix starts looking like this. And then If you have a rotating monitor where there's paid downstream, it gets even more complicated, right? So this is like kind of like the traditional representation of what is going on when we think about it. Even this like relatively simple sort of monitoring arrangement where I have all these farmers who are cracking and shirking, and then there's, in this case, this is a monitor where the monitor is actually chosen from among one of these farmers, right, on a rotating basis. So if you interpret this using the open games formalism, once again, these are pictorial representations. Underneath the hood, these are all sort of computational, actually. You have a simple plot. It has I'm going to sort of say A here is just a kind of the farmer's own decision with respect to like, this is the amount of water they can, whether to choose to crack or flood, add in a box with arbitrary other decision factors, and then sort of this is the amount of water I'm going to consume, right? And then in some sense the amount of food or sort of crop I'm going to then produce out of the plot. So you can stack these together, and this is kind of a picture of the unadorned sort of exploitative situation. I just have farmers and plots, right? And then it's actually, this representation has the nice advantage of actually looking like a canal, which is why we actually originally chose this, at least partly. You can tag in the monitor earnings and effort here. So plot 1, plot 2, plot 3 via farmer 1, farmer 2, farmer 3 incentives. And then if you wanted to edit this, you can sort of say, okay, I'm going to add in another box, basically like sort of conditional function here, to sort of describe what the monitor effort actually looks like. And then actually D in this case is a description of what you see in practice in these settings. So in practice, what happens is oftentimes what these farmers do is they assign a kind of barren plot at the very bottom of the canal, right? And they sort of award this to this randomly chosen monitor who is selected, of course, from among the farmers, who is then given the right to farm this plot. So this is actually the thing you see in practice, right? And it's relatively, and I'll just say like this is precisely how you kind of represent it through this compositional game theory sort of structure. You can also, this is a third example. Maybe just really quickly. So this example, partly the idea is like it's trying to illustrate how you do these things within a actual realistic sort of governance situation, how you iterate between different designs, and then how you sort of use substitution and composition in order to construct these larger social institutions and these social designs. In this case, this is a different composition operator called branching, where I might have a decision maker, in this case, who's trying to think about, okay, should I use a kind of wage labor for, let's say, my farm, or should I have a worker share on my farm? So it's like a very common kind of decision point where you're thinking, do I pay my workers directly, or do I say like, you get 50% of the profits, right? And this is just a kind of a way of illustrating all the things that are going on and the sort of like the decision points that need to be considered as this decision maker is thinking about whether, how much of the share the landlords make, what the underlying game is being played here versus the game that's being played here, right? You can stack many, many of these in order to sort of model the role of a decision maker in these kinds of complicated games. Okay, some quick takeaways. Compositional game theory, or any kind of programming language, is not a magic bullet, right? You need to go in there with some idea of what the situation is. You need to kind of understand like who the agents are, what their roles are, what decisions each one of them own, or they own, before you can really start doing any of this, right? So once again, it doesn't magically solve social institutions. It is, however, a better abstraction for thinking about like, how do we stick all these things together, both as a modeling exercise as well as a design or prototyping exercise. It does not give us better abstractions for designing payoffs, right? So those big, complicated matrices I showed you, partly to scare you, it does not help us design better versions of those things. You still need to do like a lot of fine tweaking to sort of say like, oh, why is this payoff matrix model this social institution better? However, equilibrium checking, at least at this stage, is still pretty useful, even though it's still quite far from automatic optimization. And of course, the engine sort of retains that sort of ability to check for Nash equilibria. There's a lot of rapid prototyping that needs to happen. How am I doing on time?
You have
15 minutes, right?
12 minutes until questions.
Okay. There's a lot of rapid prototyping that needs to happen on the, so to enable the rapid prototyping that we're kind of advertising with things like this, it still needs actually a lot of production side engineering, but we believe the potential is there. And last one, this is more internally for us. It was kind of magical when we sort of put all this into a bunch of Haskell code, and it kind of just magically works. It's really just showing that like the advantage of first starting with the math and then implementing that as a programming language. Okay, a more realistic and more recent example is some work that we've been doing with lawyers, in particular at Stanford. So if you look at the way that legal contracts are designed today, there's an existing process by which any contract is drafted, and it almost never begins with the way you would write a paper, at least you used to write a paper in maybe like the 2000s, of just drafting them up from beginning to end. What almost always happens within an actual legal firm is you start with a bunch of contract clauses, i.e. boilerplate, or maybe you start with sometimes with the whole contract, and then you sort of compose these clauses using a set of form builders to form an actual legal contract. This then goes through a process of redlining, so you send it to your partner or your counterparty or your counterparty's lawyers, most often, with various changes. These are then sort of integrated into the contract. There are a bunch of references to other contracts or laws, which are sort of put into these laws, and then this follows a set of client consultations, right? So there's a quite involved process when any time you try to draft or deliver a new legal contract between a set of parties. And what we want to kind of like, or maybe what my provocation here with you is just imagine if that was a kind of software engineering. What would it look like to turn contract drafting into a kind of software engineering practice? What you want, sort of most logically, you try to convert boilerplate into sort of software modules. You take these clause composition practices into combinators. Redlining would look more like kind of like automated testing. So I would test these clauses, see what happens with them. References to other contract or laws would become kind of external library calls. And then client consultations this is a little bit more contentious, but it looks, what in my mind looks more like agile development. It's kind of like fast iteration over contracts. And the idea, of course, is that here we can use compositional game theory, and this is the subject of the paper, to form contract drafting, to redesign contract drafting as a kind of engineering or contract engineering. So in this work, what we did is we built something off of the loggood data set. So this is a data set of clauses. This is the clause library that is not freely accessible, unfortunately, but we managed to set up a deal with them to, so basically what loggood has, it's kind of structured in, so this is an example of a sale of goods paper, sale of goods contract. And then you have different delivery locations. So delivery location here is a clause, and then I can choose between like the shipper's locations and the purchase location. I can choose different packaging and shipping clauses. And it's the nice thing here, I'll just kind of briefly mention, is they also assign a kind of score or sense of like how favorable is it to whichever party, in this case to the seller or the purchaser, right? So this is the kind of data set we worked with. And we took the loggood data set, this is a kind of just another sort of version of the sale of goods contract, indicating all the different clause categories, and for each clause category, the set of clause options that were attached to them. And then for every single one of these, we built an open game. So for every single favorable, neutral, favorable to purchase or product warranty, for each one of these clause categories, we built an open game representation of one of these clauses. So for example, this is the one for inspection. This is the favorable to seller inspection clause. So this is the kind of like pictorial representation of, okay, there's some shipment here, the buyer needs to sort of inspect it, then to decide whether, okay, am I going to Am I going to confirm that this is okay, that the quality of the product is good, or do I not confirm, right? So in some sense, there's like a relatively simple function, a relatively simple game that is being played between the buyer and seller here, but it plugs into a much larger thing, which is effectively the entire contract, right? The actual, and this is just like to give you an example, what the actual sort of inspection clause looks like when you read it. And this is another one. These things get quite long. It is not easy and not, how do I say it? It's not necessarily super fast to build the individual games, right? The payoff comes, of course, when you sort of stick them all together into larger games. Oh, sorry, this is just another example of, in this case, limited liability settlement of a game that we built for this one, where there's a damage function to the liability, and then, sorry, yeah, this is the Y diagram representation. The payoff here is that you can take game clauses that live over here, which are simpler in this graph, and you can compose them into a bunch of contracts which allow you to kind of explore the contract space of that game. And this is actually this is actually only 5% of the contract space. If I gave you all the contracts, it would just be a blue blob. But the point is, this actually allows you to kind of explore, at least a little bit, to some degree, the kind of the structure of that sort of space of institutions. So you can sort of see not only large-scale statistics in terms of things like how biased they are versus how less biased they are when you compose these clauses, but it allows you to think about like, oh, what is the structure of these spaces? That really we haven't really been able to ask these kinds of questions before at any kind of scale, certainly not for the scale of like real legal contracts.
So, Joshua, could I ask, I'm just trying to so what exactly is the contract space? Is like sequences of clauses? Is that how I should be thinking? So it's kind of space of all clauses which are consistent with the rules that you set up?
Yes.
Okay.
Yes, that is all. Yeah. It's literally just sticking a bunch of clauses together.
But there's no semantic information a priori. It's kind of the compositional game structure leads you into a contract space which may or may not have kind of...
Yes. I mean, it's in some sense, the contract space is even bigger than we illustrate here because you can make all sorts of like word-by-word edits, and you can change the definitions. These institutional design spaces, like, it's truly ginormous. This is at least just a proxy for some of the complexity that happens when we think about, at least from a lawyer's perspective, when we design these and choose between clauses. So what we're seeing now is we're hitting new kinds of scalability limits. And we're finding actually, for example, I'll just the main point here is that it's actually equilibrium checking. So the entire idea of natural equilibrium, you kind of have to throw out the window when you sort of get to games of these scale, because there's literally hundreds to thousands of these equilibria in any sort of decent game. And you're never going to be able to sort of check all of them. And even checking, like, if you know this is equilibrium, like, what does that matter? Like, how does that help you really sort of decide or make decisions about like whether this particular scenario or this particular contract is better or not? And I'm going to skip over this because of time, but we've done a lot of thought about how do we actually incorporate this into real practices around contract drafting. In particular, the emphasis here is on how to integrate it into existing technology stacks that are used by lawyers already. Last example, the Y commerce safe. So I'm not going to go into, so this is SAFE stands for a Simple Agreement for Future Equity. This is a common sort of tool used by startups to take investment. And what we did is we built the entire thing as using code, and then we converted it into a smart contract so that you can now take money safely as a kind of like a DAO or a blockchain-based organization. So effectively, and this is actually getting adopted as an open standard by the ecosystem so that people can flow money more safely using this existing sort of institutional design in this sort of more code-based environment. There's a lot of future work here. I won't go too deeply into it. There's a exciting work on the formal verification front for AI safety. We're exploring, so I mentioned earlier how it's really hard still to build large reward functions. There's a lot of work in different parts of computational social science to kind of like figure out how do we infer these large reward functions, and I think that's some really exciting work that we are just getting started on doing. So this kind of summarizes CGT, and I'm going to sort of rush through very quickly some of the more kind of like philosophical takeaways about why this is important. So this talk is, in some sense, a talk where we start with social science, we use math, and then we convert social science, or parts of social science, into code, right? And this is like very, very sort of, step back and like, okay, this is kind of the direction where we're taking things. And why does code matter? Code matters because it regulates people, right? I talked earlier about governance in terms of laws, norms, and markings of code. Code in here directly changes the way that we interact, for example, that we behave in platforms. But code, in many ways, is also kind of changing or intermediating the way that society itself functions at all, right? Code is now changing the way that laws work, that markets work, that norms work, and of course, code is implicated in all sorts of ways in which like more code is produced. In many places, so I like to study places like World of Warcraft or DAOs or just like the different kind of Slacks that we communicate with each other. IPAM communicates almost exclusively through a Slack, all the people kind of the core group participants. And these things, code is constitutive of the way that society functions. But there's so many ways in which like these societies, these things built out of code really, really fail. I'll just mention that for me, the fundamental issue here, and I've been sort of harping on this over the past couple months, is that governance is really, really still fundamentally slow in these kinds of settings, and it's still really expensive. How can we change that so that we can, I think, hopefully work a little bit faster? I was very, very much inspired by Ian's talk yesterday. And for me, it's kind of the difference between the traditional form of sort of social science where I'm just making a lot of observations. I think this kind of work is getting better, right? The richness of our data is getting way better. Our ability to analyze better is getting way better. But really, like when we think about interventions, constructing these kind of apparatuses, I think we are nowhere close, and I feel like we are nowhere close to where animal behavior is, where many, many different fields of science are in constructing these kinds of interventional structures so that we can do better work on these human social systems. And I feel that the reason we study code, the reason it's so important to start thinking and building these kinds of programming languages and other kinds of scaled up infrastructure is so that we can get to these kinds of interventional systems. Yes, and that is it. Thank you.